you can use two form. Okay, you can use the shear flow Q multiplied by ds. Okay, so ds is the distance moving in this direction. Okay. Or you can use F is equal to both limits point A to point B. You can use the shear stress multiplied by thickness ds. Okay, so this is our thickness. Again, the thickness over here is geometry perpendicular to the shear force. Okay, and just to quickly remind you that Q is equal to VQ over I. Okay, so the units over here is Newton per meter, where the shear stress is equal to VQ over IT. Okay, the units is in Newton per meter square. Okay, so that's it for the theory. Okay, that's it. Okay, so why that's it? Because I already taught you how to design the shear flow. To design the shear flow is very similar to the shear force. Okay, okay. So now we are going to look at example number 1. Okay, we're going to look at example number we're going to look at example number 1. Okay, so this is the cross-section view of our structure. Okay, so example 1. Is the cross-section view of our structure, and I want you to, so they ask us to determine the shear center O of a thin wall beam of uniform thickness having the cross section shown. Okay, so what we are doing down here is very specifically for thin wall. Now there's one thing I want you all to observe. Okay, every year I have the same problem with questions like this. Okay, I want you all to take note how the geometry has been measured. Okay, so what do I mean by how? If you look at if you look at 2A down here, okay, 2A is measured from the center of the vertical member going down here. Can you see when I draw the line where it ends? Right? It is not on the edges where it's measured. Okay, it's at the center of the thickness. Okay, so I want you to see this. Okay, like most of the time when even I started picking up this topic, I was not so observant. So don't be like me. Look and see nothing. Okay, don't do that. Okay, don't be like me. Okay, so when you observe this, be aware of where the centroid or how the distance is measured. I'll give you another example. Is when we do the horizontal, it's measured exactly at the center. You can see now, right? Okay, it's not measured at the edges. Okay, so I want you to I think most important thing is I want you to observe that. Okay, now, so the first thing that we do for structure, so now you're aware of the geometry, how they measure. So while doing this example, the first thing we're going to do is we're going to design the how the forces are flowing. Okay, so we know that the web controls the forces, so we know that forces will be going down this way, right? Then we'll go this way, then we'll go this way. Likewise, it will go this way. Okay, so these are the forces, how it's going to be flowing. Okay, so as I said, when I just realized that this is really useful for thin wall, the previous chapter or previous section when I taught that it's under symmetrical loading. Okay, because they did not say that design the shear flow first. Okay, it's to here I learn. Okay, that's how I'm teaching you guys now. So from here, we are going to divide. Okay, so we design. So the first thing I'm going to write down here, note how the dimension were done or were made. Okay, so take note of that. I have question. Hold on, I have a question. What do you mean? Don't be like that. I totally wish I could do that. Are you cheeky sort, Matthew? and then the next one is design. No, not design. Determine the flow of the shear force. Okay, so again, the web controls the direction of the force. Okay, then the next thing I'm going to write down the solution procedure. Okay, so we have done two things already. So the solution procedure is as follows. Okay, so the solution procedure. The math is really easy for this. Okay, once we go into the math, you say is that it? So we are going to find the second moment of area. Okay, then this is followed by determine the first moment of area. Again, first moment of area is usually the troublesome one. Which is the formula we're going to use is Q is equal to A Y bar. Okay, about each section. Okay, then we are going to apply the formula where shear stress is equal to VQ over IT. Okay, and as usual, I always teach this. Okay, in the very first section of the shear force and up to the very last one, we still take note that V and I are constant. If you start dividing your V based on the section you look at, it's really difficult. So we still take V and I constant. And then after that, we are going to determine F. Okay, we're going to determine F, which is which are going to be equal to the shear stress, integrate the shear stress multiplied by the cross or increment of the area. Okay, and then finally, we're going to take moment about point C, okay, to find the position of the shear center. Okay, so let's start. Okay, so let's start finding the first moment of area. Okay, sorry, I'll move so that you can still write the top. Okay, so we have our now. I'm doing this because I want to show you what geometry to take. Okay, what geometry to take. So this is, I know you guys all know how to do this, but I want to show you what geometry to take. Y, Z, and X. Okay. So we know that IZZ is going to be twice IAB. Why twice IAB? Because AB and FG have the same geometry and are in the same orientation. Okay. And plus by twice I BD, right? Again, the geometry and orientation of BD and EF are the same. That's why we take it twice. And then we're going to plus ID. And I'm going to put a small note down here that IAB is equal to IFG and IBD is equal to IEF. Okay. So now we do our IZZ. So we're going to have twice the width is T A cube over 12. Okay. And then we're going to plus, okay, we're going to plus by the cross-sectional area is TA, right? And then the distance is equal to A is 3A over 2. Okay, and this is squared. Okay, so you can see the width is T, the depth we take up to the distance A. Okay, we don't take A minus T divided by 2. Okay, we take up to the distance A. Okay, then the next one plus twice again. Okay, now the width is 2A T cube over 12. Okay, and then plus by 2A, the width is 2A multiplied by T. Okay, and then the distance is A squared. Okay. So that is for BD and EF. Okay. And then the last one, we are going to plus by the width, which is T. Then we have 2A cubed over 12. So that is for DE. Okay, that is for D. So there's one thing we can get rid of or remove is this term over here, right? Is almost equal to 0. This is because the thickness is what? Q. Okay, so imagine if you have 3 millimeters. Okay, the thickness is very small. So anything to which is the T to the power of 3, you can drop it. Okay, it's because T cube is small. or it's very small. Okay. Okay. T cube is very small. So we do the, so you can drop this term over here because it is very small, so we can drop it. Okay, so this will become any TA cube. Okay, there's 2 TA cube, so you have 1/6 over TA cube plus by 1/6 over TA cube, so 1/6 1/6 plus 1/6 is 2/3. Okay, yeah, I need to check my calculator. My math is not that good. Okay. So you get 2 TA cube or A cube T divided over 3. So what I've done is